All right. Hello, everyone, and welcome. My name is Wetzels, and I'm a security researcher with Forescout's Federal Labs. And today I will be talking about a bundle of OT vulnerabilities we uncovered, dubbed ICEFALL. So first, about a little bit about Federal Labs. We're a part of Forescout, which offers a visibility assessment and control platform for enterprise, OT, IoT, and IOMT environments. Federal Labs is involved in threat intelligence and vulnerability research. And in the past, we've performed large-scale vulnerability research into TCP/IP stacks, medical supply components, and conceptual ransomware for IoT and OT. So, as a lot of you are likely well aware, more than a decade ago, Digital Bond initiated Project Basecamp, which was modeled after the Firesheep project and aimed to show just how pervasive the lack of basic security controls in ICS equipment was. They looked into multiple products by multiple vendors and found what is by now common knowledge. OT products lack the most basic security controls. This lack of basic security controls has its roots in the historical deployment of this stuff in trusted air-gapped networks. But this situation is by now a distant past. IT and OT are more interconnected than ever before, and even wireless and cloud technologies are making headway in this space. Now, in the past decade, a lot has changed in OT security as well. First of all, in terms of awareness and recognition of this problem, and secondly, with the advent of various standards-driven security efforts, such as IEC 62443, NERC CIP, and so forth. But time and again, trivial vulnerabilities continue to pop up in OT products. And since we get a lot of customer asks to look into and support specific OT systems, we set out to do a checkup of the progress made on Insecure by Design by taking a sizable sample of actively deployed OT products and investigating their security posture. The reason why we focused on basic security issues is because real-world attackers have shown that they abuse this stuff in practice, building frameworks for manipulating inherently insecure protocols and abusing sensitive native functionality on PLCs. Now, this is one of the most well-known issues in OT, right? So why revisit it? Well, the problem is that risk management is complicated by any sort of opacity. And if you want to know whether progress is being made on this front in the actual install base, or what is actually under the hood of a particular security control, and whether a product is to be considered insecure by design or not, you'll have to dig a little bit deeper. You cannot simply assume that every proprietary system that you encounter is and will remain equally broken to all the stuff that we've seen in the past. Now, security mechanisms are sometimes, for example, retrofitted on insecure protocols, and authentication implementations can change over time. So what has been broken in the past might not be broken anymore, or it might still be broken, but in a very different way. Plus, it's not enough to know that something is insecure in general, which means very little. You need to know in what way something is insecure. After all, there's a fairly big difference between being able to change a set point on a device or gaining remote code execution on it. And this kind of info is necessary if you want to justify the right compensating controls, because you can't make informed decisions based on speculation derived from general truths alone. For example, consider making decisions around segmentation and hardening. If I'm faced with the choice to let some proprietary protocol through a firewall and maybe expose myself to all kinds of risks that I'd need to mitigate with VPN tunnels and network re-architecting, I'd like to know what kind of risks I'm actually exposing myself to first before I make those decisions. And if I'm relying on the vendor's advertised security features, so maybe I can save on some compensating controls, I'd like to have some idea of their robustness before I make that decision as well. If all of these systems are just black boxes to me and there is no public documentation of if something is insecure and how exactly it's insecure, I have two options, which is either blindly trusting a vendor and I'm going to have a lot of unaddressed risk, or I can just default to assuming that everything is insecure in the worst possible way and I'm going to need a very big budget. So let's start with an overview of these issues that we uncovered. In total, We uncovered 56 issues affecting more than 10 vendors, and this includes DCSs such as the Emerson DeltaV innovation systems, safety controllers like the Honeywell Safety Manager, PLCs such as the Saia Burgess VCD, the Omron Sysmac, and the Yokogawa Stardom. And of the vulnerabilities we uncovered, the majority consisted of compromise of credentials and firmware manipulation issues, followed by remote code execution and configuration manipulation. So a lot of these issues were fairly trivial issues, low-hanging fruit, that was still present in new releases of firmware and systems that are still in active use in the install base. Now, we disclose these issues to vendors through CISA, providing a disclosure deadline of more than 90 days ahead of publication. And in some cases, we extended the deadline if the situation called for it. Unfortunately, some vendors only started investigating our reports very close to the publication deadline. And as a result, some issues and responses are still in disclosure currently. In addition, some vendors requested details to be restricted to product bulletins only. Luckily, in other cases, we had experiences with vendors that were a little more supple, and that even led to speeding up of internal secure protocol development effort, which is always an interesting win in this regard. CISA maintains a dedicated page with detailed mitigations and affected versions that you can see on the slide. However, none of the advisories that have been published, nor this presentation, will disclose the full technical details of these issues for the obvious reasons. So in order to get an impression of how many systems were impacted by these issues, we performed some open source intelligence, including on Showdown, which showed that several thousand vulnerable devices were exposed to the internet. In addition, we looked at our own device cloud, which holds data of tens of thousands of customer devices, and found that manufacturing, healthcare, and government facilities were most represented, though certain critical systems were heavily represented in oil and gas and utilities as well. We also found that the majority of affected product families that we looked at had some form of security certification, and even though the issues that they suffered from were fairly trivial. This is problematic because while obviously security certifications aren't a guarantee of a product being unhackable, there's nuance to the levels at which they get certified. However, certification is often seen as a seal of approval of meeting a certain minimum bar. And in the case of certain products, that was simply not the case, and that leads to a false sense of security. Now, there are several issues contributing to this problem, which is the effort required to certify and to recertify products, especially at the higher certification levels, which sometimes leads vendors to not recertify a product. You just get it certified once and then don't do the recertification effort, but they advertise it as based on this particular standard instead. Secondly, the target of evaluation is often fairly limited, and the security definitions in the standards can be quite opaque. And finally, many certification efforts perform a lot of functional testing. So a security requirement is tested to be present or not, but no indication of robustness is obtained within the limited amount of time dedicated to this evaluation effort. And this holds all the more so for proprietary protocols about which the auditor will know nothing. So having some sort of advisory for security issues relating to this or that feature in a product can serve as a future reference for auditors who don't have the required SME knowledge during the certification trajectory. So let's take a deeper dive into a recurring category of issues: broken authentication schemes and improper fixes for them. While a lot of OT systems lack any security controls to begin with, it's become more common over the past decade to integrate at least some sort of authentication scheme on sensitive operator or engineering interfaces. In practice, these are often of subpar quality, however. Now, the first example I want to walk you through is the Siemens WinCC OA SCADA system. It's a popular SCADA system used in oil and gas, water management, power generation, and places like CERN. It has an operator UI, which essentially talks to a dedicated proxy by wrapping a proprietary insecure protocol called PVSS in TLS. And then the proxy unwraps it again and talks to these various components of the SCADA system in the back using this PVSS protocol. So essentially, it's a way to have some sort of a security wrapper around an insecure by design protocol. Now, in order for an operator to authenticate, there are 3 different modes. First of which is client-side authentication. This is the default mode prior to version 3.17, and it is preferred for SSO integration. The second mode is server-side authentication, which is the default starting from 3.17, but is sometimes switched out in favor of client-side authentication for SSO reasons. And then finally, there's Kerberos authentication. Now, the issue with this client-side authentication mode that's fairly popular is that it stores the credentials as points in the SCADA database. And the client just sends PVSS requests for these credentials, fetches them to the operator UI application, and then validates them locally, for example, against an Active Directory. But the attacker can obviously just skip all this by writing their own malicious client, which talks to this proxy, transports PVSS over this proxy, and then just interacts with the database in any way it wants, or maybe even fetches the credentials that are stored there. So this is an example of an authentication mode that you'd be inclined to not use, especially when, the default has become server-side authentication. But then if you want integration with SSO, it's very popular to do it in this way through client-side authentication. So there's a reason why you might want to opt for this, even in the newest versions of WinCC OA, but that exposes you to various issues that you might not be aware of if you do not know how this works under the hood. Next thing we took a look at was the Motorola MDLC protocol, which is a SCADA to R2U1 protocol that can be transported over a variety of channels, such as IP, serial, radio, microwave, you name it. It doesn't have explicit authentication features, but there are 2 pre-shared key-based encryption modes. So essentially, if you want to talk to one of these R2Us and the encryption mode is enabled, you need to possess the right pre-shared key to encrypt the packet. So, the R2U can decrypt it and say this is a valid packet. Now, in newer RTUs, there's the AS256 modes. In older RTUs, however, including the AS1000 RTU, which is still widely deployed, there is a mode that is essentially the tiny encryption algorithm in the ECB mode of operation. Now, this mode was also supported by newer RTUs for reasons of backward compatibility or networks with mixed RTUs up until recently because of the disclosure. Of course, using any block cipher in ECB mode means that you're opening yourself up to various types of attacks, non-plain text attacks, block swapping attacks, because it doesn't guarantee integrity and confidentiality above the block level, which is nicely illustrated by the notorious ECB penguin on the right of the slide, where you can see that, you have these cryptographic assurances at the block level, but they don't hold above the block level because it's just block after block after block. This essentially means that if you're using this TEA ECB mode of encryption, you're opening yourself up to various types of attacks that are not immediately clear because it's not publicly documented that it actually uses this particular algorithm in this particular mode of operation, which makes it all the harder to do some sort of risk management around this. Next, there are the Saia Burgess PCD PLLs, used a lot in machine automation, building automation, also sometimes in gas management. And they use the SBUS protocol, which is originally a serial master-slave protocol. This protocol does have explicit authentication, and that essentially works by writing to a static address. So you have a data point with a static address, and you authenticate by writing to it. Unfortunately, what you write to it is a 32-bit hash of the password, and that's derived from essentially concatenating 2 CRC16 hashes of the password. And this is trivially insecure in multiple ways. It's vulnerable to a ton of collisions because it's not a cryptographic hash. It's replayable because there's no nonce involved. So if I observe it over the wire, I can just replay it and I don't even need to know the password. And on top of that, the whole mechanism works based on MAC and IP based whitelisting. So what essentially happens is that once I authenticate, the PLC puts me in a whitelist, but it's built on top of a UDP protocol. So you're still left with all the issues related to that, regardless of the lack of quality of the mechanism. And if you had a more mature mechanism, you could have maybe done it in such a way that you cryptographically couple the authentication phase to any subsequent messages. So you have some sort of signing of these messages, and then it doesn't matter that you're using UDP, but they didn't do that. So regardless of the authentication, you have this secondary issue. Another interesting case with some overlap here are the Emerson ControlWave PLCs, and they're very popular in oil and gas, used a lot in pipelining infrastructure. They have a proprietary protocol called BSAP IP, which is an IP flavor of an older serial protocol by predecessor Bristol Babcock RTUs. It has password authentication for engineering operations, like starting and stopping the PLC and downloading logic, but again, enforces this using a MAC IP-based whitelist on a UDP protocol. So there you go already. On top of that, there are 3 authentication modes. Historically, only simple authentication, which is just a plain text password, broken in obvious way. Then they had a secure authentication mode where the PLC sends you an 8-bit key and you encrypt the password using that 8-bit key and send it back to the PLC, which, I mean, is broken in many ways. I mean, an 8-bit key is way too small, but also the key is sent to you in plain text. So, you know, if I can sniff traffic, I just see it coming to me and I can decrypt the password, and that is that. Then currently they are using secure mode 2, which is undocumented, but it's essentially the same as secure mode, except with a bigger key and a different algorithm. So now the PLC sends you a 64-bit key, you encrypt the password, and then you send it back to the PLC again. This is fundamentally bad design, 3 times over, and it speaks to a fundamental misunderstanding of how a challenge response mechanism is supposed to work. This could have been addressed twice, once when you introduced secure mode, then when you introduced secure mode 2, but it wasn't done. So unfortunately, 2 missed chances. According to Emerson, however, these are not vulnerabilities. They feel these issues are adequately addressed in the ControlWave manual, which basically says that if you want enhanced security, you can install a VPN and a firewall. Now, of course, enhanced security kind of implies that existing controls offer some form of basic security, which, in my opinion, is not the case. On top of that, the proposed reference design, which you can see on the right of the slide, it doesn't offer any protection against this issue at the site level itself. So what it proposes is you have the remote location where the engineering workstation is, and then you have the satellite site where the PLC lives, and you put a site-to-site VPN connection between them. But if you have any sort of compromise at the site location where, you know, the ControlWave is, and there isn't adequate segmentation there, which you might not do because you're led to believe that, you know, maybe this authentication is good enough, especially if I introduce this site-to-site VPN, then you have residual risk there, which is unaddressed. So not considering this a vulnerability and not mentioning what kind of quality of security you can expect of secure mode 2 might lead to accepting more risk than you actually have an appetite for. And that's unfortunate in my opinion. So an example of an incomplete rather than an improper bug fix would be the Yokogawa Stardom PLCs, which are very big in mining. They have a telnet maintenance interface that has had multiple prior issues with hard-coded credentials in 2018. And even though these issues were fixed, we found another set of hard-coded credentials affecting duplex controllers specifically. And the fact that the same issue affecting the same interface, but in a slightly different part of the firmware, was left in there after fixing 2 similar cases kind of suggests that bug fixing was treated as a one-off. So a bug gets reported and the engineer is tasked with fixing this specific bug, and that is that. Rather than being followed up with variant hunting, where you look for, okay, so we've had this issue, you know, twice. Are there any other hard-coded credentials within this code base? And that is the way you'd want to do that. But unfortunately, that apparently hasn't happened here. Finally, we found an example pointing towards a similar lack of variant hunting with the Emerson DeltaV DCS controllers. It's a very big DCS system used a lot in oil and gas. And these controllers are essentially configured rather than programmed with a strategy download from an integrated workstation and server environment. Now, first of all, most controllers up to the most recent version had hard-coded credentials for the so-called read-only telnet interface, which is a limited maintenance interface. In addition, several other hard-coded credentials were present were technically tied to FTP and SSH maintenance interfaces that were disabled by default. So very limited risk. Unfortunately, and this was not mentioned in the Emerson advisory, if you manage to get access to these controllers through another channel, perhaps a code execution vulnerability or some kind of other shell access, you could use these hard-coded credentials for local privilege escalation. And that is a factor that unfortunately wasn't mentioned. In addition to these hard-coded credentials, there is a maintenance telnet interface, and that offers access to a shell on these controllers. This interface uses an insecure authentication algorithm that is present on the M controllers, on the S controllers, on the P controllers, on the safety instrumented controllers, up to a very recent version, after which it was silently patched. And this authentication algorithm consists essentially of a homebrew crypto algorithm, which is not really cryptographically secure in any way. But on top of that, there's no secret being used. There's no secret key. There's no secret negotiated. Instead, it relies on a predictable seed smaller than 16 bits. So as soon as an attacker reverse engineers this mechanism, they can reproduce it and they get shell access to these controllers, which is even worse than being able to download a malicious strategy to it because you have very low level access at that point. What's interesting is that this is not the first time that DeltaV has suffered from hard-coded credential issues either. They suffered from these issues in 2014 on a different interface, and that kind of shows that they too did not follow this up with variant hunting across different parts of this system. And that apparently is a recurring issue. So all of these examples lead us to the question, when is something actually secure by design? Now, most standards have some functional requirements. Something shall have capability X or capability Y. It shall not do Z. But they offer no guidance on how to make this robust in a technically explicit manner. In this research alone, we found 22 CVEs related to broken authentication, while if we look at a selection of similar issues on different products from the last 5 years, we can easily find 28 CVEs with similar root causes. And this suggests that although some progress is being made in retrofitting or adding these security controls on these particular systems, it's very hard to trust the quality of these controls. They're essentially broken across the board, and this is not a particular fault of any individual vendor. It happens time and again among all of them. In addition, being secure by design isn't enough. Things need to be secure by default, rather than relying on some how to harden guidance hidden somewhere at the end of a manual. Also, bug fixes ought to address the root cause of an issue. They shouldn't just replace one hard-coded credential with another. They should address the actual root cause, and it should be followed by variant hunting. If you get reported one particular issue or two particular issues over the years, that should trigger an investigation saying, is this a recurring issue among this particular code base? So you can eliminate it instead of having just this ad hoc fixing cycle depending on the attention of an individual researcher. And I would think that this is what a standard certified SDLC should be able to guarantee, right? So to summarize this part, please, no more Potemkin security. Subpar security controls can result in a false sense of security that can actually be worse than a clear sense of insecurity, or at least you will be able to take these compensating controls because you know how insecure you are, instead of relying on controls that are far more porous than you might be led to believe. Secondly, secure by design and secure by default can only work with clear, technically explicit minimum requirements and in-depth, independent validation that goes beyond just functional testing. Now, during the research, there's some classes of issues that require a little bit of more nuance when you're looking at them and their particular impact. I will take a brief look at a few of these issues where if you just look at the vulnerability in isolation, you might be led to believe that it's actually worse than it is, considering mitigations that might be available. Or maybe you might be aware of certain standard type of mitigations for these issues, but because of all kinds of caveats, it doesn't quite apply in that manner in that particular case. And it is kind of a showcase for the depth of familiarity with a particular system that you need to have in order to be able to make the right call on what level of risk a particular issue actually poses to you. So first of all, there's the issue with supply chain vulnerabilities. In the past few years, we've seen more and more supply chain issues across the technology stack in OT, from RTOSs, SDKs, and protocol stacks to runtimes and remote access solutions. Now, what happens all too often is that a vulnerability affecting some supply chain component high up, but that is discovered in one particular product that just uses this component, doesn't make its way up the chain again and then back down to all the other offended vendors. Sometimes it's because discoverers of an issue are unaware of the issue, that it's actually part of a third-party component instead of this particular product. So it just gets reported for the one product and then nobody ever learns where it's actually located. In other cases, the vendors of that third-party component themselves might not have a complete overview of their entire downstream supply chain because there's intermediate system integrators, there are white label vendors and OEMs that maybe take this particular component, that take some embedded board, they slap it together, they resell it to a lot of different vendors that put just a brand sticker and some additional software on it. And at each of these layers, there is only a partial view of the supply chain. So it requires complicated coordination, complicated visibility into these supply chains in order to get that information out to all these different parties. And these kind of situations lead to unnecessary vulnerability collisions and risk blindness. An example of this that we encountered during this research a lot is the ProConOS runtime. This is an IEC 6.11313 runtime, similar to, for example, CodeSys or Isograph, originally by KWsoft, now owned by Phoenix Contact. It's used by their products, but also by many OEMs, system integrators, and white label vendors under many different integration conditions. You might, for example, have different runtime versions. You might, for example, have different protocols that belong to this runtime. You have the SOCOM protocol, you have the ADE protocol, but you can also use these runtimes with your own proprietary protocol. So one thing we frequently encountered when we were at a customer and they had a particular PLC or a particular PLC family in an environment was that after some investigation, it turned out to run ProConOS. But this wasn't immediately clear from the outside because the PLC didn't advertise that. It wasn't mentioned, maybe in the advertising materials. Maybe it didn't use the conventional protocols that you'd use for fingerprinting, but it used their own proprietary protocol. And the problem here is that if you want to get an idea of the security posture of a particular PLC, and you don't know these third-party components that are in there, they might have a long history of well-known vulnerabilities. In the case of ProConOS, those are unauthenticated engineering protocols where you can start and stop the PLC and download logic to it without authentication. And you can get remote code execution through unsigned logic. So you can just download your logic, it's unsigned, it's unauthenticated to do the logic, and you can get code execution on a PLC. But if you don't know you're using this runtime, you're oblivious to the fact that you're exposed to all these risks, especially given that public proof of concepts have been available for some of these issues for years. But either no CVs were assigned to some of them, or the corresponding CVs were only assigned to Phoenix Contact products. So due to the lack of software bills of materials in this case, vulnerabilities get rediscovered a lot. And an example here is that there's a CVE from 2016 for the Yokogawa Stardom PLCs, which on the surface seems unrelated to any of them. All right, should be good now. So yeah, during this work, we identified various additional affected parties, which you can see on the right of the slide. These include some big names like ABB, KUKA, Advantech, Yaskawa. And this is far from complete. This is just a sample selection that we identified. There are way more parties using this. And we suggested that these parties would be included in the original CVs. So the CVs that were originally issued for Phoenix Contact, augment them with these different parties that are also affected so that people using these systems know that they're exposed to this kind of risk. Unfortunately, this hasn't happened yet for various reasons. Might still happen in the future, but unfortunately, it hasn't happened yet. But this ideally is the way you deal with these sort of issues. Next example are firmware updates. Malicious firmware updates in OT context are a little bit of a mixed bag to the attacker, since on the one hand, they're noisy, as they require a controller reboot, which will likely interrupt the operational process and trigger alarms. But on the other hand, they're very powerful, since they allow for persistence and mask breaking of controllers. Of all the products that we looked at, only 51% had any sort of authentication for performing these updates, and only 22% performed some sort of firmware signing. Now, the majority of firmware updates took place over Ethernet, which combined with the lack of authentication and signing is particularly worrying. But it was a minority which only did firmware updates over SD card, USB, or serial, where at least the risk is reduced to a compromised engineering workstation or media converter. However, it is important to note that even if you do sign your firmware, you need to do this in the right way, which means signing by the vendor and validating by the device in end-to-end fashion in an asymmetric fashion. An example where this doesn't go completely right are the Emerson DeltaV DCS controllers. These controllers speak a variety of unauthenticated proprietary protocols, which are spoken between the controllers and between workstations and servers and the controllers. And they allow for various things, starting and stopping the controller, firmware manipulation, configuration changes, and so on. In addition, prior to version 14.3, controller firmwares are unsigned and only use CRC. Now, Emerson considered this issue resolved in 14.3 because the update tool there now that resides on the engineering workstation that you can see on the top of the bottom right of the slide, this update tool now validates the RSA signature that is present in the firmware manifest file before flashing the firmware to the controller. But this really only protects the firmware as it travels from the vendor to the engineering workstation. It doesn't protect against any attacker that directly talks to these controllers, that just bypasses the engineering workstation and manages to directly speak these protocols to this controller. It also doesn't protect against a compromised engineering workstation, which, is a prime crown jewel target in OT environments. And even though if you compromise an EWS, you can already do a lot, you'd still not want immediately that an attacker is able to have the most low-level type of access to those controllers. You want that extra barrier that is enforced by the controller itself there. Now, Emerson considers this issue further mitigated because in the DeltaV reference architecture, which is shown on the bottom right of the slide, the controllers in the area control network portion are segmented from the workstations and the servers by using the firewall IPD component that is part of the DeltaV solution. Since controllers can be software locked, that means that you put them in a software lock state and then certain engineering operations can't take place anymore. You need to unlock them by sending an unlock message over one of these protocols. And essentially what the firewall IPD does is it drops this message. So it doesn't go from the workstations or servers to the controllers unless a physical override is initiated on the firewall IPD or the controllers themselves. So technically a good measure to reduce risk there in a certain manner. However, an attacker can still wait until a legitimate engineering window where these messages are no longer dropped by the firewall in order to send one of these messages and then perform their engineering actions otherwise. An attacker can also just compromise the EWS and wait until a legitimate engineering window and push the malicious firmware that way, because the validation only happens on the EWS itself. So the problem here is that while the risk is somewhat mitigated, there's still residual risk left. And if you do not explicitly address this, if you do not explicitly mention this is the residual risk that is left, and these are the attacker scenarios that are still possible, then people might blindly accept something that they're not actually willing to accept. So a second point that requires some nuance here are vulnerabilities related to unsigned PLC logic. Now, generally speaking, as shown on the bottom of the slide, the logic which you use to program a PLC is typically compiled to either native machine code or to some sort of a proprietary bytecode or scripting language. This is then transferred to the PLC, where there is a logic runtime that executes it either directly through a code loader, or it runs it on a VM or a script interpreter, or maybe it dispatches it to a dedicated logic code processor, which can be a microcontroller, or an ASIC, or an FPGA, or something in that direction. In the controllers that we looked at, the vast majority executes their logic as native machine code. None of them sign this logic, so there's maybe some sort of authentication on the engineering interface, but there's no signing on the logic, and only a handful apply some sort of sandboxing to this native machine code that gets executed. This is particularly dangerous because most PLCs have a real-time operating system that does not have support for memory or privilege segmentation. And they also do not have, in many cases, the hardware or the software to instruct the hardware to do these things, to use an MPU or an MMU to enforce segmentation between different tasks or between different compartments on the PLC. So once you get code execution, it's very quickly game over in terms of what you can do internally on the PLC there. And it matters that this is different from PLCs with a different architecture, because if all I can do is run unauthenticated, unsigned logic, but I'm restricted to, a bytecode interpreter, I will first have to break out of this virtual machine. And that's an extra hurdle that has to be taken there. So the impact of different unsigned logic downloads is not always the same, obviously. An example of this that we encountered in the research is the Omron Sysmac family. They have the older C family, which consists of CS, CG, and CP controllers. And here the logic is compiled to a proprietary bytecode, which is executed by a dedicated ASIC, as you can see in the middle of the slide. On the newer N families, however, for reasons of economy and reasons of modifiability, logic is now, like on most modern PLCs, compiled to an unsigned x86 machine code format. And this means that even if in both cases the logic that gets downloaded is unsigned, you have a little bit of a difference in impact. And actually, the older C families has a lesser impact here because you're constrained to whatever the bytecode on the ASIC can do, which is very different than being able to execute unconstrained low-level machine code on the newer N series. And this is like a kind of nuance that you can only really get a grip on if you know a little bit about the internals of these PLCs. Another example of the difference in impact is with the Honeywell Safety Manager SIS. This is a SIL3 safety controller used in various critical applications, similar to the Schneider TreeConnects. The engineering software, which is called Safety Station, compiles safety instrumented functions, which essentially are safety loop diagrams, to unsigned native machine code again. And this is then wrapped in a project file format and downloaded to the controller using, again, an unauthenticated protocol called Safety Builder. After receiving this download, the communication module sends it over the backplane to the CPU module, which executes it directly on the CPU, leading to unconstrained code execution in the heart of this safety controller. Interestingly, however, even though there are similar issues in the newer S300 family, this doesn't apply because there the CIF diagrams are compiled to mnemonic bytecode. And in inverse way to the Omron Sysmac, here the newer family uses a bytecode interpreter and as such has a lesser impact for any unwanted malicious logic downloads than would be on the older Safety Manager families. Finally, there's some nuance to be made regarding mode switches. These are very traditional defense in OT against malicious configuration, logic, downloads, firmware updates, and so on. And they essentially consist of a physical switch on the controller which regulates the PLC mode of operation. And this essentially enforces that before you can do certain engineering operations, you need someone with physical presence rather than an attacker who only has logical access to the network. And you have these different modes, which can be run mode, where the logic is operational and executing, but you cannot do certain engineering operations. Or you have program mode, where maybe the logic is not running, but you can do these engineering operations. Sometimes you have a remote mode, where you can do both. And these mode switches come in various forms. Sometimes they come with a physical key, as you can see on the left with the famous Triconix key switch. Sometimes it's just a toggle button, as you can see on some of the Schneider Electric Modicon families. Now, what's important here is that not all mode switches offer the kind of protection that you're looking for here. There's several pitfalls. First of all, you want a distinct run and program mode. These need to be mutually exclusive. So if you're running the logic, you should not be able to do the engineering. And if you are able to do the engineering, the logic should not be running. That's also why you want to avoid a remote mode, because it's very seductive to an engineer to just leave it permanently in remote mode, where you can do the engineering and it's running, while if you have mutually exclusive modes, you force the engineer, you either do the maintenance and the engineering, or you have it running. And once you're done engineering, if you want to get it up running again, you put it in run mode, and that way it's not up to the engineer's own discipline to enforce this mode switch state. So, we looked at the support for these types of switches, and you can see on the right of the slide that the vast majority of the products we look at do not have this strict mutually exclusive separation between these modes of operation. Only 17% actually had this kind of hard distinction. Secondly, you want to avoid having a virtual switch setting in the engineering software, where sometimes you have a physical mode switch, but in the engineering software, you can override it. You can just take engineering actions. You can say, go to run mode, go to program mode, and that overrides whatever is happening in the mode switch on the PLC. You don't want any functionality like that. Third, you should be aware of exception modes, which configure the PLC to ignore the switch settings. And finally, some PLCs are not configured to require these switch checks prior to engineering operations by default. You need to explicitly enable that. So be aware of that as well. An example of this is the Emerson ControlWave PLC that we talked about a little bit earlier. Firmware updates here are, again, unsigned, and this is especially troubling given that they happen over this BSEP IP protocol we talked about with all its authentication issues. Again, unfortunately, Emerson didn't consider this a vulnerability either, because they said there is a key switch that can be set to run mode. There's a configuration setting which can be set to disable any remote changes. The problem is that this key switch also has a remote mode, and that essentially means that this barrier of defense puts all the onus on risk control on the discipline of the engineers. Because if they screw up there and they leave it in remote mode, you don't have proper authentication to prevent the downloads. You don't have firmware signing to prevent malicious firmware. And then, it's left to the individual discipline of the engineer there, which puts a lot of risk on potential human failure. The other option that they have is the application lock setting. The problem there is that it is not set by default, so you need to dig into the manual and you need to set this setting during commissioning, and that essentially disables all remote engineering. So that makes the decision like, look, we don't do remote engineering on this particular PLC, which is sacrificing a lot of engineering effort there. A final example of why there's a lot of ifs and buts to mode switches is the Honeywell Safety Manager. We just saw that logic downloads there are unsigned and unauthenticated, and they can give an attacker remote code execution on the Safety Manager CPU module. Luckily, there's quite a few key switches involved here. The Safety Manager is an example of a very good mode switch design where there's mutually exclusive run and idle modes. Before downloading the logic or firmware, the switch must be set to idle. And then after the downloading, you need to trigger a fault reset, which means turning another key switch on the body and key module. Except, however, when there is a setting enabled that is called remote load or remote reset. And enabling these features needs a one-time physical key turn during initialization and commissioning and stuff like that. But if this has been enabled for historical reasons, and you have not documented this in your ISMS, this might be a major blind spot because you might have enabled this at some point for remote engineering purposes that, where physical presence was cumbersome or impossible or some reason. You haven't documented it in your ISMS. Maybe you have it somewhere in some engineering document. But then when you started, doing your risk management over these particular systems, you assumed, we're protected because we got the key switches, even though, you don't have the overview of whether or not this feature was enabled. So this is one of these nuances where you need to know quite a lot about the individual system. And you cannot just rely on, is there a key switch and are we using this key switch in the proper fashion? So with that in mind, let's take a quick look at some of the reverse engineering effort that went into understanding many of the proprietary protocols and systems that we analyzed as part of this research, so we can get a little bit of a feeling for the attacker effort required to replicate some of these capabilities. Now, in terms of the SCADA, DCS, and engineering software, these were mostly Windows software packages that were typically very large, multiple gigabytes of code, hundreds of DLLs, and a lot of complicated features like MFC code, ATL code, COM, inter-process communication, stuff like that. The vast majority of code for both Windows software and firmware was written in C++, which always makes reversing a bit more cumbersome. And while the embedded devices typically resembled non-consumer devices, a lot of ARM and PowerPC combined with VxWorks and QNX, for example, there were quite a few regional outliers. Like, for example, you saw it in a lot of like the Asian systems. You see operating systems like OS9 or Itron with a lot of like Super H architecture systems, and that requires building some custom tool chains there. All in all, the systems we looked at represent a selection of typical non-trivial OT code bases to reverse engineer. Regardless, we found that reverse engineering a single proprietary protocol typically took between a day and 2 weeks of reverse engineering effort, while a complex multi-protocol system could take up to 6 months of reverse engineering effort to truly understand what is all going on in these protocols and in these firmwares and these parts of the different software components. While this is obviously quite a bit of effort and it requires certain skills, it is within the capabilities of a fairly small team with the right incentives, rather than being the sole domain of large organizations with dozens of highly skilled engineers, as is sometimes the picture that is painted for developing these kind of capabilities. And that brings us to mitigations and conclusions. So mitigating these issues is no trivial task and will require a multi-pronged effort, starting with ensuring that you have good asset inventories, you do monitoring with DPI capabilities. Secondly, you should enforce segmentation controls in the network, informed by good protocol knowledge rather than just white lists of ports. You should use native hardening capabilities like these mode switches on the PLCs and consult SME expertise on these specific devices, what the particular risks are and how it actually works under the hood. And finally, asset owners should actively procure for secure by design products while working towards consequence reduction via cyber PHA and CCE methodologies. In conclusion, we've seen that insecure by design issues continue to persist in production install bases, despite more than a decade of hardening efforts. And in order to address this, we will also need to get a clearer picture of what secure by design actually means. Since, one, many security controls that have been added, to be fair, do turn out to be trivially broken across the board, not with any individual vendor. It's mostly across the board. Products with these broken controls continue to be certified at some level. And in many cases, glaring vulnerabilities are sometimes still dismissed because there's some advice pointing to compensating controls, even if the risk is not actually fully controlled for, and there's still some unmentioned residual risk present there. We also see quite a few security retrofits on top of legacy stuff that misses the point, like doing IP-based ACLs on top of UDP protocols. Fixes frequently don't actually address the root cause, and when they do, and something is fixed, identical vulnerabilities in the same code bases aren't picked up because of a lack of variant hunting, which suggests immature secure development life cycles. And finally, devices should be secure by default, rather than giving the system integrator enough rope to hang themselves with through complicated commissioning and initialization procedures. So I'd like to close out with a common call to action that's been made a million times before, but warrants repeating nonetheless. To device manufacturers, they should really start properly securing OT devices and protocols. Asset owners should actively procure for secure products and hold manufacturers to higher standards than even they've been doing through the standards-driven efforts. The wider security community should continue to ensure that security controls that pop up in OT products are actually robust and not just some form of Potemkin security. And that's that. Thank you for listening, and if there's any questions, I'll take them now.
Right. Thank you. So yours is actually available with us on Zoom. So can I just check? Can you hear us?
Hi, I can hear you. Can you hear me?
Yes, we can hear you. Fantastic. So we've got about 5 to 10 minutes. So let's answer some questions. So the first question is this culture of insecure design in OT due to interoperability and backwards compatibility requirements, or due to a lack of business case for security patching and redesigning secure systems?
So I think in a large factor is that, these systems, they have initially been designed as insecure by design for historical reasons. And then as you asked, many of these systems need to maintain backwards compatibility both to older components, to other systems which they need some integration capabilities with, as well as the inability to change certain protocols. So certain insecure by design features continue to persist even in newer systems, and might have some security controls bolted on top, but redesigning these entire systems or even components that are part of a larger system without breaking compatibility is very hard to do. So yeah, this is for a large part largely due to backwards compatibility and legacy concerns, rather than there being no business case, which increasingly there is.
I see. All right. Before we move on to the next question, actually, may I know by raising your hand who asked this question? Yeah, so actually you got the top most voted question, so please proceed to the back later to receive a small prize. All right, the next question. It seems that insecure by design is the default standard for most of the OT industry, and the manufacturers seems like they do not really care about it at all. What would it take for it to actually raise or move the security standards higher?
So I think there's several things that would make them move the needle on the security posture of these systems. But what we've seen is that while standards-driven efforts have helped, they in many cases have also helped to kind of mystify the actual robustness of these controls. So what would really help is more pressure from actually the customer base, from the asset owners, that should demand that vendors offer a higher level of security than they have been offering. And they could do that by making something like secure procurement the default. So if you are procuring for new equipment, whether it's a greenfield project, a brownfield project, whatever, integrate a security test or a penetration test or some sort of in-depth technical investigation of the security controls of this product into your RFP. As part of the acquisition process, that would definitely help driving up the pressure on vendors beyond just checking boxes.
All right. Last two questions, very quickly. With virtual mode switches, in your experience, are vendors aware of the limitations, as in incorrectly assumed to be physical and not virtual?
So the vendors are definitely aware when a mode switch is virtual. The problem is that these are often treated in the last few years, decade plus, as a security measure, while they're not necessarily designed as such. They're designed as an operational safety measure, essentially, to ensure that while you're working on the device, it's not running, or to ensure that you can only do these modifications once you have the proper work order and stuff like that. So from a purely operational point of view, a virtual switch is good enough, because like the engineer goes over there, he sets the PLC in programming mode, then does his changes and takes it out of programming mode again. But if you treat this as a security measure where you want this to be some sort of a hard lock, you need to be aware, is this actually a physical switch or not? And the vendor will definitely know this. But this lack of knowledge is often on part of the asset owners and the operators and the engineers. So they often don't completely know how a product works under the hood, and that kind of becomes a problem when you start using these native features as security measures.
All right. Now, the very last question. Are the physical keys themselves considered of the security of the device? Or is it just a proof of physical presence? How bad is it to always leave the key in the machine?
Yeah, that's a very good question. I'd say that depends on your threat model. I'd say in general, the biggest added benefit is a proof of physical presence, which is why in some systems it's just a button and not an actual key. The vast majority of keys that you encounter that are used for mode switches are not secure keys. Like you can just, open them with a paper clip. It doesn't even take lockpicking skills. So from a physical security point of view, where you're trying to guard against, someone who might have physical access to the plant, it's not that much of a security measure. It's really to enforce a proof of physical presence against an attacker who only has remote logical network access.
All right. And these are all the questions that we have. Thank you very much for your time, Jos, all the way from the Netherlands. Right. Can we have a round of applause for him?